Good evening. This is Applied Thermodynamics course problem solving session for week 1. The course tutors are Professor Niranjan Sahu and Professor Pranab K. Mondal. And this is the first week, and in this week we'll go through the basics of the thermodynamics before building upon how to apply them for different systems. So, so this week I have prepared problems on the first law, second law, some examples on the thermodynamics part, and we'll see how to solve those. And initially we'll see some MCQ questions and then numerical types. And to give you a brief about this week, so to go back and have a flashback on the thermodynamics or the first law and second law. So starting with thermodynamics is nothing but your energy in transit. So you apply this to study some system, to see its behavior or to see how well it performs or so on, and you for that you will apply the laws which are defined in the thermodynamics. So you would have studied basically the two laws, first law and second law. There is also a third law, but we study mostly the first law and second law. So before going to this first law and second law, we need to understand, to study something, we need to understand what are the parts of it. So what is a system, and what is boundary, what is a surrounding. So a system is something which we are interested in, or what we need to study on. So that is system, and rest of it apart from that is the surrounding, and the one which separates these two is the boundary. And then you have state properties, and then so what is a state? A state is any state. You can say what is defined by some pressure or temperature. So you can say where exactly, or what is it. So to define that to any system, you need a state. So that which defines is that state. Then you have properties which is called intensive or extensive properties. So intensive properties are independent of your mass, and extensive properties are dependent. So if you see examples of an intensive property or density, for example, so how can you easily find out whether it's an intensive property or extensive property? You just divide that into two system and see if the value of that property changes. So if you say water, you split that water into two parts, the density will remain same. So it is irrespective of the mass or the size of the system. So that is an intensive and extensive property. And then if you go to system, a type of system, a closed system, open system, or an isolated system. So open system, you have interaction of mass which is going in and going out, and there is also energy interaction. If you are a closed system, you don't have mass transfers, but you have energy transfer. An isolated system is a special case of closed system where there is no energy interaction as well, heat transfer. Energy interaction, and so our whole universe is an isolated system. And then you come for first law. First law says your energy is constant. So say any this thing, there is only transfer of energy, and that energy will remain constant. And any for two states, when you have a process, so the net heat transfer minus the net work transfer will give you the change in the internal energy of the system. So this is defined by the first law. And then second law states two statements. You have Kelvin-Planck statement and Clausius statement. So one defines there is no you cannot have heat transfer with just a single reservoir. Another, to transfer heat from a lower to higher temperature, you need to supply some work. And then that from there you also get entropy properties, and we'll see some problems on how to calculate entropy center. So with that we'll see some problems. Before that, if you have any doubts, you can ask. Windows weak. Okay, so then I'll move on with the questions which I've prepared. So first we'll see some small, just to brief up, small MCQ type problems, and then we'll see numerical type problems. So first is in a free expansion process, choose the statement of for heat and work transfer. So you have starting A, the total work done is 0, the total heat transfer is 0, work done is 0 but heat increases, both statement A and B. So if you see in a free expansion process, there is no restriction. So you're just in a vacuum, you're trying to expand the gas. Sorry, if you have a balloon filled with gas, you pop it into vacuum. So that is an example of free expansion. So in that case, you will not have any work done, and also you will not have any heat transfer happening. So your answer is option D. A second, on a hot summer day, a student turns his fan on when he leaves his room in the morning. When he returns in the evening, what will be the room's temperature? Assume all the doors and windows are kept closed. So you're staying in your room, your windows, everything are closed, you are just switched on the fan and left. So what do you think will happen? The room will get cooler, warmer, or there will be no change? So the answer will be B, warmer. So if you try to put an energy balance across the room, so if you see, the only energy which is coming in is the electricity, but this being windows, everything is closed, you assume there is no transfer. So there is a net energy which is coming in, but there is nothing which is going out. So in that case, your internal energy of the system will rise. So internal energy is so Q. For first law, the change in internal energy is W minus Q. So your Q is 0. So your net work, which is the electrical work which you are giving in, is equal to change in internal energy. So MCV T2 minus T1. So your temperature will rise. So it will become warmer. So the density of water is maximum at 4 degrees Celsius. True or false? So answer is true. So if you see, this is how the density variation of the water is with respect to temperature when you plot. So when you're going from 10 degrees, you are cooling it, so your density will increase and then start decreasing. So that's why when you go below 4, your ice basically expands in water. So that will reduce the volume, total volume is increasing, so your density is reducing. So, but any normal fluid will, with reducing temperature, your density will increase. But water is a peculiar case where at 4 degree it will have a maximum and then it will start dropping. So the next question is, which of the following thermodynamic parameters are considered as intensive property? So you have 4. So which are of this is intensive property? A, specific volume, B, mass, C, volume, and D, internal energy. So the answer is option A, specific volume. So anything specific is you are dividing it with respect to mass. So an intensive property is an independent property, independent with respect to mass. So answer is specific volume, and also it's 1 by rho or 1 by density. So density is also an intensive property, which I gave talked just before. So specific volume is the answer, and applying the same concept. So mass, if you divide into 2 parts, you each part will have a different mass, and similarly for volume, and similarly for internal energy. So energy is you can have specific internal energy that is independent of mass. Here it's just the internal energy, so that will be an extensive property. So these are some examples of the type of system. So you have a cup and saucer which is placed uh, so in that case you have both heat transfer and also the vapors which is coming out, and that is a mass transfer. So this is an open type of system. Now you have a lid which you are closing on the top of the saucer cup. So you have heat transfer which is occurring, but there is no mass transfer because this is closed. Similarly, you have a thermos flask. Then in this case, uh, there is no heat transfer and there is no mass transfer. So what do you think will be? You have a pressure vessel, and you have a liquid natural gas which is stored, which is at minus 160 degrees Celsius. So what do you think that will be? So ideal case, it should be a just a similar case of an heat transfer. Sorry, a thermos flask. So you have because it is minus 160 degrees, the vessel will be insulated. So ideally speaking, that should be a closed system. But there will be some heat which is leaking in. So if you going to a normal case, so there will be some heat which is leak, and because of that, the vapor will form and the pressure will start rising. So at that case, you will also have some pressure vent valves up the top. So that will release the pressure to keep that in a certain state. So you can try to, based on the assumptions which you make, you can put it in all three of it. So the next question is, the sum of heat and work transfer will be 0 if a system returned to its initial state having gone through series of processes. So they are saying sum of heat transfer and work transfer that will become 0 if a system is a cyclic process. Is it true or false? So answer is true. So that is basically the definition of first law. And internal energy, this is for a process. So cyclic process, the initial and final state is same. So internal energy being a state property will also be become 0. So its net heat transfer will be equal to net work transfer. So just like the previous example, instead of a fan, you have a fridge. So what do you think? And that fridge door is open and it's a closed room. So what do you think will happen? The temperature of the room will gradually increase. No effect on room temperature will realize. The temperature of the room will decrease to refrigerator temperature. Any of the above depending upon the refrigerator type. So if you see, this is also similar to what we saw in the previous. So irrespective if this is fridge or an air conditioner or whatever, if you see it has a energy balance across the room, there is just an input energy which is coming in and there is nothing which is going out. So the total internal energy will again increase and your temperature of the room will increase. And you can think it in the other way, but you can say that my fridge which is the inside should be colder. So if you see how a refrigerator works, so refrigerator operates between the low temperature and higher temperature, and you supply some work to remove heat from the lower temperature and dump it in the higher temperature reservoir. So refrigerator, the inside cabin is your lower temperature reservoir and outside room is your higher temperature reservoir. And if you see the heat which is removed from the inside cabin will be some Q, but which is dumped out to hotter reservoir will be Q plus W. So you see net heat transfer which is occurring inside is again W. So your temperature will increase. So next is exergy is the minimum, the amount of work a device can deliver without violating the laws of thermodynamics. So answer is true. Sorry, exergy is the maximum amount. So exergy is the maximum amount which you can get. So it's false. A system delivers the maximum possible work as it undergoes a reversible process from the specified initial state to the state of its environment or the dead state. So this amount of work which can get is the work potential, and it's also called as exergy. Okay, few more MCQs are there. So what will happen to the temperature of air coming out from a punctured ball? Will it become hotter, no change, become cooler, or D, uncertain? So ball, a football, you pump in, and so the air which is there inside the ball is pressurized. So if you it's a punctured, so the air is coming out. So this is Joule-Thomson's effect. So it will become cooler. Only certain fluids are there which will become hotter at room condition, normal your pressure conditions, NPT conditions, which will be hotter. For example, hydrogen, helium. So this will be if it's filled with hydrogen and it's at hydrogen gas, so that will become hotter. So this is being filled with air, so it will become cooler. So moving on to the next question. For a spontaneous process, choose the correct option from the following expression for entropy of system and surrounding. So the system minus entropy change of surrounding is greater than 0. The entropy of surrounding should be greater than 0. System plus surrounding should be greater than 0, and system greater than 0. So answer is option C. So what basically says is the second law, your net entropy should be total entropy change should be greater than 0. So your system and surrounding both will come into play. So for an isolated system, the value of entropy never decreases. True and false. So it's an isolated system. So for an isolated system, it's true. Your entropy always increases, and for isolated system, because you cannot have any interaction outside, so that whatever entropy is generated inside should always go in the direction of increasing entropy, so it cannot never decrease. So next question is, a person is cooking food for his family in a pan that is A, uncovered, B, covered with a light lid, and C, covered with a heavy lid. For which case will the cooking time be shortest? So what do you think? You have a pan, you are cooking something, so which is the best action which can be taken to reduce your cooking time? Option is C. So what basically it does is, you are closing the system and you are applying heat. So your internal energy is increasing, and your temperature and pressure both increases in that case. So your content of the pan will cook faster at a higher pressure and temperature. So that's why you use a cooker. So pressure cookers. So it's the concept of using a pressure cooker. So you reduce much time using a pressure cooker. So that's why people use dal and everything is cooked in a pressure cooker, because that takes too much time to get cooked. So moving on, a 600 megawatt steam power plant, which is cooled by a nearby river, has a thermal efficiency of 40%. Determine the rate of heat transfer to the river water. So you have 600 megawatts steam power plant. So that's the amount of work which you are getting from the steam power plant. So which is cooled by a nearby river, and this has a thermal efficiency of 40%. So efficiency is nothing but your work done divided by the heat supplied. So because your efficiency is 40%, and your work done is 600 megawatts. So that is amount of work which you're getting from the plant, divided by your Q which you supply. So from there we will find out the energy which has to be supplied is 1500 megawatts. So your Q rejected will be applying first law again. So net heat transfer is equal to net work transfer. So work transfer is 600 and heat transfer in is 1500. So Q out will be 900 megawatts. So answer is option A, 900 megawatts. The next question is, does latent heat, which is HFG is Hg minus Hf, is saturated vapor enthalpy and is saturated liquid enthalpy, change with pressure? The answer is yes, it will change. So if you see a pH diagram of any fluid, so this is how it will look. So this is for a water. So this being a pure fluid, so you can write it as pH also, because it's a constant line at for pure fluids. So with increasing temperature or increasing pressure, your latent heat reduces, and at the top it will have a critical point where your latent heat will become zero. So there you cannot distinguish the phase, whether it's a liquid or vapor. So both will look identical. So yes, it does. The latent heat does change with respect to pressure or temperature. This is not visible. Okay, I'll move on to the next question. Let's see if can change. Just share a different file. So the question is, the driver of a car of total mass n driving at the speed c must slow down to stop over a given distance l. So the car is driven down a hill with a slope corresponding to an angle alpha. The internal energy of the car at rest after cooling is the same as at the initial state. So the air drag is neglected. There is no slip on the wheels on the road. So you have basically you are at the top of a hill and you are descending, and you have to stop the car at a certain given distance l. And what they are saying is, after which the car comes to rest and the car is cooled down, so that energy state is internal energy is equal to what it was at the top. So there is no air drag. You can neglect the air drag, and there is no slip between the wheel and the road. So in that case, what is asked is, there's certain things which is given. The fixed braking distance is 100 meter, so you have to stop in that 100 meter distance. The hill slope is given as tan alpha is 0.07. The initial speed of the car, which is the speed at the top, is 72 km per hour. The total mass of the car is 1000 kg. And the acceleration gravity is 9.81 meter per second square. So we have to calculate the change in the car total internal energy, calculate the heat Q generated during the braking. So let's see how to solve this. So if you apply first law, so the work done here is change in work done. So initially this is at 0. The final state, initially it is at certain potential energy and certain uh, velocity. So finally you have velocity 0 and you are assuming that 100 meter you are at the bottom of the jet. So you have come to rest. So the final energy is 0 and initially you possessed some internal energy and potential energy. So minus mv square by 2 minus mgh. So h is nothing but you need to find out the vertical height. So you know the slant height 100 meter to which you have come, and you also know the angle. So alpha is tan inverse 0.07, so it's 4 degrees. So from there we can find out the vertical height h, and the velocity is 72 kilometer per hour. So you are converting it to meters per second. So it is 20 meters per second, and mass you know 1000 kgs. So substituting all values here, so get W as minus 268.7 kilojoule. So you know what is asked is the heat generated during the breaking. So we know the total internal energy U is become 0 because the initial and final state is same. So then applying first law to the whole process. So your change in internal energy is 0. So your heat transfer should be equal to your work transfer. So your work heat transfer will become 268.7 kilojoule. So what they, so okay, we know now have values. So what does this signify? So what actually is happening is you are at the top. So you have to reduce. So you will apply brakes. So you apply brakes, and normally brakes are, you have shoe brakes which will go and on the disc or the wheel drums, it will try to push and it will try to reduce the speed. So this is generates, there is a friction between these two, and this will generate heat. So whatever energy you are putting to slow down the car is dissipated as heat. So you need 268.7 kilojoule of energy to apply brakes to reduce the speed, and that is dissipated as heat to bring it down again back to the initial internal energy state. So that's what is signified here. Okay, moving on to the next question. A rigid container of volume 400 liter. Any question in the previous problem? If you have any questions, you can raise or you can ask at that. Okay, so moving on to the next question. A rigid container of volume 400 liter is divided into two equal compartments A and B by a thin partition. Both compartments contain air. Compartment A is at 2 megapascal and 200 degrees Celsius, and compartment B is at 200 kilopascal and 100 degrees Celsius. The partition ruptures and the contents eventually reach an equilibrium state by losing heat to the ambient at 27 degrees Celsius. So we have to determine final pressure, heat lost to the surrounding, and the entropy generated. So we'll see, go by pitch and pass we have pitches. So first we have a rigid container. So that container rigid, you cannot damage it, or you cannot, so that is a fixed container. That container is divided into two parts. The whole container volume is 400 liter. So both compartment or the both parts of the container has air in it, and there is a difference in pressure and temperature. So compartment A pressure is 2 megapascal and compartment B is at 200 kilopascal, and compartment A temperature is 200 degrees Celsius and here it's 100 degrees Celsius. So there is both pressure and temperature differences. So now the partition which is there between the structure, equilibrium state while losing heat to the ambient. So after losing heat, it will reach the ambient temperature, which is 27 degrees Celsius. So determine the final pressure, heat lost to the surrounding, and entropy generated. So first we'll estimate the mass which is there in each of the compartment. Considering compartment A, and this air, we can assume it to be an ideal gas, and we'll apply an ideal gas law to estimate the mass of air which is present in the compartment A portion of the vessel. So compartment A, MA equals to PV by RT. So pressure we know, which is at 2 megapascal, or 2 into 10 power 6 pascals. So 2000 into 10 power 3, that's 2 into 10 power 6, and volume is given as so it's divided into two equal parts. So each is at 200 liters. So converting that into meter cube is 0.2 meter cube. So divide by R. R is universal gas constant by molecular weight. So for air, it is 288.68 into temperature. So temperature given is 200 degrees Celsius. So converting it to Kelvin is 200 plus 273. This will give you 473. So substituting this, so mass of air in compartment A is 2.93 Kelvin, 93 kgs. So similarly, we can apply it to compartment B and estimate mass of B. So here pressure is 2 bar, and so 2 into 10 power 5 into 0.2 volume, so equal volumes. So 0.2 divided by R, and temperature is 100. So 100 plus 273, 373. So this comes out to be 0.3715 kg. So now this partition is ruptured and both gets mixed. Since the final temperature T2 is equal to the ambient temperature, the final pressure can be calculated using again an ideal gas law. So now instead of 200 liter volume, it's a 400 liter volume, and your mass is the total mass of each of the compartments. So MA plus ME is the total mass, and from there we can find out the pressure. So T2 is your ambient temperature pressure, ambient temperature 27 plus 273. So that is 300, and R is known to 88.68, and volume is 400 liters, so 0.4 meter cube. And mass here you have to just add 2.93 plus 0.3715. So if you add that, your pressure will come out to be 714.81 kilopascal. Now taking the air in both the compartment as the system, applying the first law. So now this is like an as I told, the free expansion process. So it's just expanding. There is no work transfer out of the vessel. So that the work transfer is 0. So the total whatever change in internal energy is there, that is the amount of heat which will be transferred to the surrounding. So on applying there, so delta U is Q minus W. So your delta U will become mCV delta T for each of the compartment masses. So mass A into CV, the final temperature is T2, but initially it was at temperature 200, and the mass B MB is final temperature is the ambient temperature minus the initial temperature, which is 100 degrees Celsius. So substituting the values of these masses and CV 0.716, and the temperature we know, so substituting that, we will get QS minus 385.39 kilojoule. So this is the amount of heat which will be rejected to the surrounding. So now we have calculated the heat. The next part is we have to also calculate the entropy which is generated. So entropy change of the system is, so for the system, for a change in pressure and temperature, so this will be mCp ln P2 by P1 minus R ln P2 by P1. So this we can get from any of the TDS relations. So if you get du equals to TdS minus PD plus PdV. So if you substitute that and you apply ideal gas equation, so you will end up with this. So Ma Cp ln T2 by T1 minus R ln T2 by T1. So that's what we will get. Sorry. So here we know mass of air, which we have already calculated. Cp is 1.005 for air, and ln T2 we know initial temperature 200 degrees Celsius. Sorry, final temperature, ambient temperature, which is 27 plus 273, which is 300, divided by 473, which is 200 degrees Celsius, minus R ln, and again pressure. We have already found out P2, which is 714.81 kilopascal, and P1A is 2 megapascal. So substituting that, we'll get the entropy change for just the mass of air A. So similarly, we have to find for MB. That will give me the total entropy change in the system. So that comes out to be minus 696 joule per Kelvin. Now we have to find out the total entropy generated. So the entropy generated in system and the surrounding which have to take place. So system we have already found out. With the surrounding is at ambient temperature, and you are supplying it some heat. So which we have found out minus 385.39 kilojoule. So with respect to surrounding, the surrounding is gaining that heat. So it will be in positive, 385.39 into 10 power 3 divided by the temperature of the ambient. So 273 plus 27. So this will give you the entropy change in the surrounding. So adding both, we'll get the total entropy generated is 588.63 joule per Kelvin. So next is moving on to the next problem. Any doubt in the previous one? I'll just brief up. We first had the partition, so we found out individual masses of the compartments, and then we estimated the using Avogadro's law what is the final pressure when the whole vessel is at the ambient temperature, and then we found out what is the change in internal energy, and because there is no work transfer, the whole of change in internal energy is given off as heat. So then after that we found out each individual compartment's change in your entropy, so entropy generated, and you can find out the system entropy using that, which is mCp ln T2 by T1 minus R ln P2 by P1. So and then we found out the entropy change in the surrounding, and surrounding there is a constant temperature heat transfer, so Q by T. So from there we know the entropy generated in the surrounding. So we have added up both system and surrounding to find out the total entropy generated. Okay. So moving on to the next question. Consider the frictionless piston cylinder arrangement shown. Initially, the air contained in cylinder A occupies 0.0864 meter cube and is at 200 kilopascal and 300 Kelvin, while the air in cylinder B occupies 0.0398 meter cube and is at 300 Kelvin. So this is how your system is. The cross-sectional area of cylinder A and B are respectively 0.00786 meter square and 0.00393 meter square. So you have two piston cylinder arrangement with a common shaft. So and you have initial states which is being specified. So initially what is the volume occupied by A and B is given, and what are the corresponding pressure and temperature is also given. So and the cross-sectional area of the pistons of each of the pistons is also given. So now heat is supplied to cylinder A, causing the piston to move slowly downwards by 2 meter. So the total mass of the piston and connecting rod is 10 kg. So this total piston rod is 10 kg. Cylinder B is completely insulated. Pressure of the air in cylinder B after the process is 442 kilopascal. So you are supplying feed to cylinder A, because of which the cylinder is expanding and it's compressing the cylinder B. So during that process, at the end of process, your pressure at cylinder B is 442 kilopascal. Now what you have to determine is mass in cylinder A, so the mass of the fluid which is in cylinder A, initial pressure in cylinder B, mass in cylinder B, your work done by the atmosphere, work done by the piston, and then final volume in B, final temperature in B, and then work done in B. So multiple final pressure in A and final pressure temperature in A. Heat supplied when P atmospheric pressure is 100 kilopascal and G is 10 meter per second square. So we have to find out multiple steps. We'll see how to solve one by one. So starting with, we'll find out what is the mass in each of the cylinders. So what we know, so we'll go with mass cylinder A. So because there we know all pressure, volume and temperature. So the mass of air in cylinder A at initial state, using the initial state properties. So applying an ideal gas law, Ma is Pt by Rt. So pressure initially P1 for A is 200 kilopascal and temperature is 300 Kelvin and volume is 0.0864 meter cube. So substituting that, we get mass of air which is there in cylinder A is 0.2 kg. So at any instant during the process, so a force balance on the piston assembly gives, so if you apply a force balance on this piston assembly piston, you have pressure which is there exerted by cylinder A, and then there is atmospheric pressure which is acting upwards. So P minus PA will give you a net force, and then there is a force acting downwards for weight, so mass of piston into gravity, and then for piston it should be equal to piston B force, which is pressure B which is exerted upwards, and the atmospheric pressure which is exerting downwards. So P minus P atmosphere into area of piston. So this is the force balance of the piston. So if you see PA, pressure A is acting downwards, and mass weight is acting downwards, and atmospheric pressure is acting upwards for cylinder A, and the other side your atmospheric pressure is acting downwards on piston B, and your cylinder pressure B is acting upwards. So taking that sign convention into account, this is the final equation which you will get. So here we know the atmospheric pressure which is given 100 kilopascal. We know G, we are assumed to 10 meters per second square, and we know initial pressures P. So we can find out the only unknown which will be is the cylinder B pressure. So from here we can find out the initial pressure which is there in cylinder B. So substituting the values, we can find out the initial pressure in B. The expression will be like this. So P atmosphere 1 minus piston cylinder A cross sectional area divided by B cross sectional area plus initial pressure for in cylinder A into cross sectional area of A divided by cross sectional area of B plus the cylinder piston weight divided by cross sectional area of B. So substituting all values, you will get the initial pressure at cylinder B as 325.45 kilopascal. initial pressure, you know initial volume and initial temperature as given in the problem as 0.0398 meter cube and 300 Kelvin. So now you know all three properties. So you can apply the ideal gas law to estimate the mass which is present in cylinder B. So mass at cylinder B will be PV by RT. So P is 325.45 Newton per 3 and volume is 0.0398 and you know R for air is 288.68 and temperature is 300. So this will come out to be 0.15 kgs. So from this we have found out all three of the unknowns asked. So they asked to find out mass of A, mass B, and the initial pressure B. So that we have found out. So A, B, and C is found out. Next is to find out the work done. So the work interaction from the atmosphere is nothing but your P atmosphere into your delta V. So that is the your atmosphere exerting some pressure. So your work done is P into delta V, PdV. So the volume which is getting changed, that is at moment of pressure and pressure because of pressure exerted by atmosphere, that is the amount of work which the atmosphere is doing on the system. So P atmosphere into delta V of system A plus delta V of system B. So during the process they have given that the piston moves by downwards by 2 meter. So delta V atmosphere is minus 2 into A delta PA, and similarly for delta V atmosphere is this is nothing but A into H height. So that will give you the volume, area into height. So 2 into area of cylinder B. So we will know the change in volume in cylinder A and cylinder B, and we know atmospheric pressure is 100 kilopascal. On substituting, it will come out to be 786 joules. So next is we need to find out the work done in piston. So piston, the work done is the change in potential energy which is happening. So you know the weight of this piston. So mass mgh. So mg, mass of piston assembly is given as 10 kg, and g is also 10, and your change in height is the how much height which is coming down. So that is 2 or minus 2 will come out to be minus 200 joules. So that is done. Next is we found out final volume in B. So we have to find out the final volume. So final volume is, we know the initial volume which is given, which is 0.0398 meter cube. So minus the change in volume which we have already calculated. So substituting that, you will get the final volume as 0.03194. So initially it was at 0.0398. It becomes 0.03194. So next is the final temperature in B. So we now know the final pressure. Final pressure is given in the problem. It's 442.84 kilopascal, and final volume which you have calculated. We know the mass which I have already calculated. So apply an ideal gas law again. We can estimate the temperature at state 2 of the cylinder B. So substituting that values, we will find out the temperature is 327 Kelvin. So now if we apply the first law to cylinder B, we will get the change in internal energy is Q minus W. Since the cylinder B is insulated, so there will be no heat transfer. So whatever change in internal energy is there, it will be equal to the work done in cylinder B. So it will be equal to mCV delta T. So mass of B is known, CV of air is 0.72 or 721.7 joule per kg Kelvin, and the temperatures are known. So initial temperature is 300 and the final temperature which we have calculated is 327. So substituting that, we will find out work as minus 2933 joule. So you see the work is negative because the work is done on cylinder B. So you are compressing the cylinder. So if you see your final volume is 0.03195 and initially it was 0.0394. So because of cylinder A, heat supplied in cylinder A, your cylinder B is getting compressed. So your work is negative. So that is minus 2923 joules. So next is we need to find out the final pressure in cylinder A. So for that again we know the force balance in the piston. So from this and rearranging in terms of pressure in A, so this is what you get. So this expression part B, so P minus P atmosphere into cross sectional area plus your weight minus change in difference in pressure in cylinder B into cross sectional area. So this is the force which is acting in the piston. So rearranging in terms of cylinder pressure A and substituting all the values. So you know the final pressure in cylinder B which is given in the problem, you know cylinder weight, you know the cross sectional areas, you know atmospheric pressure 100 kilopascal. So substituting that, we will find out the final pressure in A is 258.7 kilopascal. So now you need to find out final volume in cylinder A. So that is because the cylinder A is expanding, so you have to add that volume. It will become 0.10212 meter cube. Using this volume and pressure, we can estimate the temperature, final temperature in cylinder A. So T2 is P2V2 by mass into R. So substituting all the values, so P2 we have found out to 58.7 kilopascal into 0.10212 divided by mass which calculated as 0.2 into R is 288.68. So this will give me temperature as 458 Kelvin. So we have found out the final volume. So next is to find out the heat transfer, heat which we have supplied to cylinder A. So again we will apply an energy balance across cylinder A. So if you apply an energy balance, so for any process, the first law, delta U is Q minus W. So Q will be your change in initial energy plus your work which we have supplied. So this will become your delta UA minus WB plus, so if you see WA is nothing but your net heat work transfer. So whatever work WA is provided, that is done in overcoming your piston, your atmospheric pressure, and also your work done in piston B. So if you see this is your cylinder A, so you are giving some heat, because of which cylinder A is producing some work. So this work is utilized in compressing B, overcoming atmospheric pressure or the work which is reduced because of atmosphere, and also the work which is done on the piston in reducing its height or changing its potential energy. So WA is nothing but minus of WB plus W piston plus W atmosphere, and change in internal energy of A is mCV delta T. So we have found out all the work done. So substituting that and the temperatures, so we will get QA is 26.714 kilojoule. So this is the amount of heat which we have supplied. Any doubts? give a recap. This being a very big problem. So starting off, we know certain initial states for cylinder A and cylinder B, and we know initial volume and initial pressure and temperature. So you are supplying some heat, because of which cylinder A expands and the piston moves down by 2 meters, and that compresses cylinder B. So this is what is happening. So first what you did is, with the known specified conditions, you found out mass in cylinder A, and then you applied an force balance across the piston. So here you have to be careful on how the pressure is acting on the cylinder. So atmospheric pressure is acting upwards in cylinder A and is acting downwards in cylinder B, and you are doing a force balance. So this is what you get with the expression, and then that you rearrange to find out the initial pressure in cylinder B. Using that and the given specified volume and temperature, you found out mass, and then you estimated what the individual work done are for atmosphere and piston, and you found out the volume. With that and the final temperature given, you found out the final temperature, and then you estimated what is the total work done on cylinder B, applying the first law. And then similarly, using the final pressure, you estimated what is the final pressure in cylinder A using the force balance. Then, and also you know how much is the change in volume. So using that, you found out the final temperature in cylinder A. With all this knowing, so we can estimate now the heat transfer occurring in cylinder A, applying an energy balance. You see that your total whatever work is generated in cylinder A is getting utilized in compressing B, piston and atmosphere. So this is what it is. So using that and substituting that, you will find out the heat supplied is 26.714 kilojoule. So here everything is positive, should not get confused in sign, because WB is already written as negative. So that is you are already taken care of the sign convention there. So here it's all just W addition. So a negative sign, the value specifies that it is consumed and WA is produced. So you should be careful in the sign conventions. So moving on, the next question is, the electronic components of a computer are cooled by air flowing through a fan mounted at the inlet of the electronics enclosure. At steady state, air enters at 20 degrees Celsius, 1 atmosphere. For noise control, the velocity of the air entering cannot exceed 1.3 meter per second. For temperature control, the temperature of the air at the exit cannot exceed 32 degrees Celsius. The electronic component and fan receive respectively 80 watts and 18 watts of electric power. Determine the smallest fan inlet area in centimeter square for which the limits on the entering air velocity and exit air temperature are met. So we'll see what exactly is happening. So we'll see in bits of, so first, what is the aim? The aim is to cool an electronic component of a computer. So it's just like the CPU, you have a fan and you have a motherboard which you have to be cool, or the processor, you have a fan over it. So that is used to reduce the temperature. So here they are saying that you can say you are sitting in an air conditioner room, so your temperature is 20 degrees Celsius and your pressure is at 1 atmosphere. So that's the atmospheric pressure. So here you have a limitation. What they are saying is, the fan cannot run too fast that the velocity is exceeding 1.3 meter per second and it's creating noise, but it cannot run slow such that your heat temperature of the air which is coming out is at higher temperature, 32 degrees. So if you increase the speed, there is a problem with noise, but if you reduce the speed, so the amount of mass of air which is coming in to cool the component, so that will increase that will reduce, and the temperature of the air which is coming out will increase. So there is a limit between the maximum and minimum which you can use. So you have to find out an optimum velocity such that it has a smallest fan inlet area. So we'll see how to solve this. So here, so area 1, A1 is defined as your velocity. Area into velocity is your volume flow rate equals mass into specific volume. So this is again will give you the volume flow rate. So from there we can find out area. Area is nothing but mass into the specific volume at inlet divided by your velocity and inlet. So this is known now. So from this we can find out area. So now we apply an energy balance across this whole electronic component. So this being an open system, we will apply the steady flow energy equation. So to find out, so this will be dCV by dt, that will become 0. We can assuming that the process is steady state. So it will become QCV minus WCV plus m dot into change in enthalpy, change in your kinetic energy, and change in potential energy. So here there is no heat transfer occurring to the surrounding directly, but the air which is there which is taking that energy. So there is no direct heat transfer from the component to the surrounding. So your Q is 0. So work done is the electrical energy which is you are giving in, which they have already specified, 80 watts for electronic component and 18 watts for fan. And then your velocity and potential energy is 0, and your velocity you are assuming it to be same. So your control volume applying this will reduce to be WCV is m dot h1 minus h2, and work done is known 98 watts. So substituting that, m dot is minus WCV divided by Cp T2 minus T1. So here that is known. So substituting this expression in A1, this is what we get, 1 by V1 into minus WCV divided by Cp T2 minus T1 into, you don't know specific volume, so but you know temperature and pressure. So assuming that air is an ideal gas, so I can write RT1 by P1. So PV is MRT, so V by M is specific volume, so specific volume will be RT by P. So this is what you get, the final expression for A1. So now there are limits on your velocity and temperature. So for this expression, so increasing V1 and T2 will decrease, but there will be an increase in noise. Since V1 cannot be cannot be greater than 1.3, should be less than or equal to 1.3 meter per second, and T2 should be 30 degrees Celsius. So substituting that here, so V is 1.3 meters per second, and you know the W energy which you are supplying, you know Cp. So assuming inlet is 20 degrees Celsius and outlet is 32 degrees Celsius, and substituting the corresponding pressure and temperatures, you will find out that your area 1 should be greater than or equal to 52 centimeters square. So the smallest fan area which you can have, such that both these conditions are satisfied, 1.3 meters per second and 32 degrees Celsius. So that is the hard limit which you cannot cross. So using that as a value, you estimate that the smallest area you can have is 52 centimeters square. Is this clear? Okay, then moving on to the next question. You have two blocks A and B of mass Ma and mass Mb and specific heat capacities Ca and Cb respectively, with initial temperatures T1A and T1B. So T1B is less than T1A. So A is the higher temperature compared to B, and these are finite masses. So it has mass, specific mass, and yes, specified mass and specific heat capacity Ca. So a reversible heat engine operates with the blocks as reservoir. Determine the final temperature and the work produced. So, assuming that you are putting a Carnot heat engine between these two finite masses, so at any instant you will have some delta QH of heat which is coming in, and you are generating some delta W of work, and delta QC is projected to B. So the at any instant it will be delta QH by TH, the temperature at that instant, because it is initially at T1A, but the temperature will reduce and it will come to some equilibrium temperature where there is no work which is generated. So there is no T and TB is basically equal. So there is no heat transfer and there is no work which is generated. So at any given instant, so this is what it will be for a reversible heat engine. Delta QH by TH equals delta QC by TC. So now if you apply the first law, so delta QH is nothing but MCP delta TH for MACA, specific it is given as CA, and similarly delta QC is MCMB CB DTC. So substituting this in the expression, this is what we get. So now if we integrate this, so we get minus MACA is varying from T1A to T2. So dTH by dTH equals MBCB, which is varying from T1B to T2, will dTC by TC. So the final temperature will be equal to, so when you integrate this, it will become ln TH T1A by T2, sorry ln T1 MACA ln T1A by T2 equals MBCB ln T2 by T1B. So, and that upon rearranging, it will become as T2 equals T1A T1B raised to power k. K is the ratio MBCB by MACA raised to power 1 by 1 plus k. So this is what you get. This is the temperature, final temperature. So using this and the work done as the total change in internal energy of system A minus a total change in internal energy in B. So that will give you the net work which is possible. So this is the total Q1 which is possible, which is transferred to the engine, and this is the total Q2 which is transferred to reservoir B. So that difference will give you the net work which is generated. So this will come out to be MACA T1A plus MBCB T1B minus T2 MACA plus MBCB. I think this is a very simple problem. So first you applied the Cauchy integral to find out the temperature. So assuming reversible process, you find out the final temperature, and then using that you apply first law to estimate the net work done. So any doubt in this problem? Okay. So moving on to next question. We have a Carnot cycle engine which receives and rejects heat with a 20 degrees Celsius temperature differential between itself and the thermal energy reservoir. The expansion and compression process have a pressure ratio of 50. For unit mass of air as a working substance, the cycle temperature limits of 1000 Kelvin and 300 Kelvin. and T naught as 280 Kelvin, determine the second law efficiency. So what it basically says is, you have a reservoir which is a temperature 1300 Kelvin, but there is a temperature difference between the reservoir and the cycle it is operating. So that temperature difference is 20 degrees Celsius, and they are saying the expansion compression process have a pressure ratio of 50. So you have to find out the second law efficiency. So your actual available energy is 1 minus T2 by T1. So this is the actual available energy, which is the heat, the temperature with the temperature which is provided, that is 1300 Kelvin. So that is 1 minus T2 by T1 into QH. So the minimum available energy required is the net work which is provided, which we can get using a reversible energy with a 20 degrees temperature difference. So from there, you find out the second law of efficiency is the available energy which you get by the actual which you can get. So here your actual work is the reversible engine, which is operating between 980 Kelvin and 320 Kelvin, and the what you can using an ideal case with no temperature difference is 1300 Kelvin. So substituting that here for same heat which is supplied, so this will become 1 minus 320 by 980 divided by 1 minus 300 by 1000. So it will be 0.63673 by 0.7. So this becomes 96.2%. So if we see, even though it's a cargo engine, so because of the temperature difference of 20 degrees Celsius, your efficiency has come down by, so this you are comparing with the Carnot, actual Carnot, which you can have, so it has come down by 3.8% for same amount of heat which you are supplying. So this is the final problem which I have. If you have any doubts, you can ask. So this is the last problem which I have prepared. If you have any doubts what we saw, you can ask. Okay, so moving on. So a container with a mass m of oxygen can move horizontally on wheels as shown in figure. So this container is subject to the following processes. So 1 to 2, there is a very slow acceleration from the state at rest to a constant speed C2. So so you have a container which is there, so there is a rigid container. So that is initially at rest, and you are slowly accelerating and bringing it to a constant speed C2. Now the second process is 2 to 3, which is brutal stop resulting from the shock against a vertical wall. And then the speed C3 becomes becoming first process is you are slowly accelerating it and bringing it to constant speed. Now this container is going and hitting at a wall and coming to rest. So that is the process 2. So what are the assumptions which has made is the container wall is infinitely rigid, so it doesn't go, it doesn't deform, so it will be intact. And second is the container is thermally insulated. So what are the data which is given is, so the initial temperature of oxygen which is there is at 20 degrees Celsius. So isochoric specific heat of oxygen CV is 0.64696, mass of oxygen is 0.1 kg, speed of container at state 2 is 100 meters per second. What is asked is determine the evolution of the internal energy and the total internal energy of the system. 2 is determine the evolution of the temperature. 3 is are the processes reversible. first one, you see, we'll go process by process. So initially assuming process 1 to 2, you see there is no heat transfer, and because the container is rigid, so it doesn't, there is no work transfer is also happening. So your internal energy is 0. So the acceleration being slow from state 1 to 2, there is no internal friction, there is dissipation. So delta is ds is 0. So change of internal energy is therefore, for this is just for the oxygen, which is 0. Now as a total system, this is being slowly accelerated. So your total system internal energy is m change in your kinetic energy. So mv square by, yeah. You have any doubt? Okay. Okay. So your total system energy is mv square by 2, change in the kinetic energy. So that comes out to be 500 joules. Second is process 2 to 3. So here the internal energy is goes and hits the wall and comes to rest. So in this case, so wall being infinitely rigid, so that doesn't undergo any deformation, so there will be no work done, and there is no heat transfer which is also happening because it's insulated. So the first law gives the change in system internal energy. So what it was there at initially, so that the energy which is gained will be same at the end of the process. So your change in internal energy is 0. But now if you see the change in internal energy is 0. So but where did the energy which it processed, the kinetic energy, goes? So that energy is going into oxygen. So that goes in erasing the internal energy of the oxygen. So delta U is mv square by 2, again the change in kinetic energy, which is 500 joules. So the change of total internal energy is, accounting for the fact that the potential energy of the system does not vary, is 500 joules. If you have a question, you can ask. Ravi, you have your hands raised. If you have any question, you can ask. You can type in if you are not able to speak. Okay. So anyway, I'll move on. If you don't have any query. So initially, what happened is, because it was moving slowly to come at a constant speed, so there is no internal friction or something which is going into the oxygen. So that energy just went into raising the total internal energy of the system. So that went in moving the container. So the oxygen internal energy didn't change, but the total system's internal energy changed. When it come to abrupt stop, this internal energy which was processed by the system, now this is no longer moving, but it was a sudden stop. This internal energy cannot dissipate anywhere else, so it went in raising the internal energy of the oxygen. So that what happened in the two processes. So how is the temperature which is changing? So initially in oxygen there is no internal energy change, so your temperature is also not changing. But in process 2 to 3, because the container came to a hard stop, the internal energy processed by the system went into raising the internal energy of the oxygen. So the oxygen, how it will raise is, it raises its temperature. So now it gets energy, so now it will raise its temperature. So the temperature change will be then the energy change is 500 joules. So 500 divided by mcp, which is given. So it will come out to be 7.697. So your change in temperature is T3 is 20 plus 7.7 degrees Celsius. This is 27.7 degrees Celsius. So the third question was, is the process reversible? So are the process reversible? So the system goes through a succession of mechanical and thermal equilibrium. So process 1, 2. So that is a reversible process because it happened very slowly. So you accelerated the vessel to a constant speed. So just like that, you can gradually reduce the speed and bring it to stop. So that process is reversible. So in that case, your mcv ln T2 by T1, you see the entropy change, that is 0. So there is no entropy which is generated. So that also says that the process is reversible. The second process 2 to 3, so that is came to an abrupt stop. So following the shock, oxygen is subjected to pressure waves which are progressively dampened because of the dissipative phenomenon of excess friction. So you have suddenly went and stopped, so you will feel a jerk, right? So you suddenly brake a car, you will feel that jerk, the sudden stop which you have come. So just like that, the oxygen molecules which are there inside will feel that pressure waves, and that it was is created because of the energy which is coming in, and that because of the viscous forces between the molecule, that energy is converted into the internal energy, and it will raise its temperature. So this process is irreversible. So if you see your change in internal energy in this case is mcv ln T3 by T2, which is 1.684 joule per Kelvin. So in this case, you have to do some amount of external work to bring back it to the initial state. So this process is not reversible, you cannot go back. So here on the right is just an plot showing how the process is happening. So 1 to 2, your it's plotted in internal energy versus entropy plot. So 1 to 2, there is no internal energy change. So your oxygen is U1, so there is no change in internal energy of the oxygen. So U1 and U2, so the oxygen is at same internal energy, but your vessel, the internal energy, the total system, so that is at higher energy U3. So that is the because of the kinetic energy possessed by the vessel. So U3 is the total energy system. So if you see 1 to 2, this is the state, there is no change. But 2 to 3, when it suddenly comes to a stop because of the shock, this process goes to state 3. So the oxygen goes to state 3, and system this thing internal energy goes the total energy of the system, internal energy is again constant. So the total energy processed is U3 at when it was constant speed. The oxygen was at U1 and U2, the system was at U3, and again when the system came to a stop after the hitting, the energy is again U3 here. So the change internal energy is not changing, but the oxygen raised its internal energy, that whatever kinetic energy was there, so that is went into raising the internal energy of the oxygen from 1 to 2 to 3. So this is what the process is. So this is if you see that is gradual, you can see that hitting and coming to a stop, the energy because of viscous, say, it's gradually raising the temperature of even though it's spontaneous and you cannot this thing, but if you see it very slowly, it's like the kinetic energy is slowly getting absorbed in the oxygen and raising its internal energy. So this is what happens. So with that I finished what the problems which I prepared for today. If you have any queries or doubts on the problems which I've solved, or uh, the questions on regarding the BIGS content, you can ask. If you don't have any queries, we can end the session. If you have any doubts or queries regarding this week's content, then you are free to ask. Again, since you have no queries, thank you for joining. We'll see in next week. So next we'll go through Rankine cycles and start with those. So thank you. So we'll end the session. Thank you for joining. Okay, then we'll close the session for everyone. Thank you.